This is the lesson about the root mean squared speed. It is lesson 8 in the thermal physics topic. These should be the things you should be able to do at the end of the lesson, and these are the spec points. So we're going to start off by looking at this thing called the root mean square speed. Now, it's a bit of a mouthful. Root mean square speed. Root means square root. Mean meaning mean. Square meaning square it. And speed meaning speed. Before we get to that, let's break it down a little bit more. And let's first of all look at this here. So this is v for velocity, and it's got this little bar on top. That bar, whenever you see that bar, that means you're looking for the mean of something. So this right here means the mean of v, the mean of the velocities. So a bar on top means that is the mean of everything under the line. So for example, let's say I had 3 particles. I would calculate the mean by doing the sum of the velocities, adding all the velocities of 3 different particles together, and dividing it by the number of particles, in this case 3. Let's say now I want to do the square of the mean velocity. So this term here, listen very carefully to the words. This is the square of the mean speed. This is the square of the mean speed, and that would be done just by adding up the numbers, dividing it by the number of those numbers, and squaring it. So it's just the square of the mean. Something slightly different now is this. So this is the mean squared speed. This is the mean of the squared of the speeds. This thing here is not the same as this thing here. Because of the position of the bar here is on top of the v, which means I find the mean of the velocities and then square that. This means I find the square of all the velocities and then find the mean of that. So it would look like this. I would do the velocity of the first particle squared, plus the velocity of the second particle squared, plus the velocity of the third particle squared, all divided by n. Hopefully you can see that this is not the same mathematical operation as that. It would give you different answers, and we'll do an example in a bit to see that. This brings us back to what I mentioned at the beginning of this slide, the root mean square speed. So this here, c is often used for velocity. It doesn't mean the speed of light here, it's just another symbol instead of v. So here we're looking at the root mean squared speed. This is the root mean square speed, often called the RMS speed. The root mean squared speed is the square root of this. So here we can see inside that square root we've got v squared and then the mean of that. So what I'm doing is I'm squaring the velocities, I'm finding the mean of the squared velocities, and then I'm square rooting that. You might be looking at this and you might be thinking, why does the square root and the squared not just cancel out? Well, it's because the mean is in between them. I can't just cancel out the squared with this square root because I'm finding the mean of the squared values. If in the square root it was this term instead of this term, then the square root and the squared would cancel out, but in this case they don't. So this term here, this is the root mean squared speed. This is what I'm talking about. So make sure you add that to your notes. And this would be calculated by doing this, the square root of the sum of all the squared speeds divided by the number of particles. So it's the square root of this here. So we can say that the root mean squared speed is the root of the mean of the square of the speeds. It's quite a mouthful, I'll say it one more time. It's the root of the mean of the square of the speeds. And we can say that if you square the root mean squared speed, then you would get back to this value here, which is this one here. This is the mean squared speeds. Let's have a look at an example and it'll make it a bit clearer. So here I've got 7 particles in a box and these are their speeds. So what is the mean speed of all these particles? Well, to work out the mean, I add up all the numbers, divide it by the number of numbers. So I'm going to do 3,000 plus 4,000 plus 2,500, etc., 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 and divide it by 7 because there's 7 particles, and I would get 4,671. Next question is, what is the square of the mean speed? Well, I will now want to work out the square of the mean. So all I'm doing is I'm just squaring the mean. So I can just square what I found out the mean was, so 4,671 squared, and that would give me 2.18 times 10 to the power of 7. Apologies, that should be a to the power of there. So that would be the square of the mean speeds. Next question, which is a harder one, is what is the mean squared speed? This means what is the mean of the squared values of all the speeds. So this is this one. This is the mean of the squared speeds. In this one, I'm squaring each value and then I add up the squares of those values and divide it by the number of values I have, the number of particles, which is 7. So in this case, to work out the mean squared speed, I would do 3,000 squared plus 4,000 squared plus 2,500 squared, etc., 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 divided by the number of particles, which is 7. And that would give me 2.42 times 10 to the power of 7. And that is slightly different to the squared mean speed value. The one we just did on question 2 was 2.18 times 10 to the power of 7. This is 2.42 times 10 to the power of 7. You see, it does not give you the same answers. They're close, but they're not the same, and that is important. So final question now. What is the root mean squared speed? I've left this down here as a reference. This was the mean speed. So this was what we found the mean speed was. This time we're looking for the root mean squared speed. So I'm looking for this. I'm square rooting the mean of the squared speeds. Remember, the square root and the square don't cancel out because the mean is in between them. So here I'm just going to square root the value we got in the previous question, square root of the mean squared speed. That was the mean squared speed, was 2.42 times 10 to the power of 7. I'm going to square root that, and I get 4,917 meters per second. So you can see that the root mean squared speed is not the same as the mean speed. That proves that this square root and square don't cancel out. So we get slightly different values, and there is a reason for that. The equation that uses this further is looking at pressure at a microscopic level, and this is the equation. You must practice this one. There will be some questions in the quiz for this week. And it is pressure times velocity equals a third times n, which is the number of molecules, m, which is the mass of a single molecule, not the mass of all molecules, and mass of a single molecule, times the mean squared speed. So this value here, this is the square of the root mean squared speed. I know there's so many words going on in this lesson, squared and root and mean. Listen to it multiple times and write it down until you understand it. This is the square of the this is the square of the root mean squared speed. So this is the mean squared speed. We will use this in a question and it should make a bit more sense. If you want the derivation, there's a really cool derivation of this equation, and I'm going to do an extra video for that, so just have a look in the description and I'll put a link to that one. It's a really nice derivation. An example of using the equation we just looked at is this. So pause the video and read the question. Okay, so here we've got a pressure of 800 kilopascals, 800 times 10 to the power of 3. We've got a number of molecules, capital N, 4.0 times 10 to the power of 25. We've got the mass of a single molecule. Remember, m is just the mass of a single molecule. Is 4.7 times 10 to the minus 26 kilograms. And the root mean squared speed of the molecules is 450. We have to calculate the volume, so V is what I don't know. So these are my variables. The equation we just looked at was this. I'm going to rearrange it because I want to work out the volume. So I rearrange it to get V equals, and I get that. And then here, we can see that the term in the equation is the mean of the squared speeds. The question gave me the root of the mean of the squared speeds. So I'm going to have to square my 450 value to get this thing here, to get the mean of the squared speeds. So putting in the numbers now, I would have a third times n, the number of particles, which is 4.0 times 10 to the power 25, times the mass of a single molecule, times the root mean squared speed squared, times 450 squared, divided by the pressure, which is 800 times 10 to the power of 3, and you should get 0.159 meters cubed, or to two significant figures, 0.16 meters cubed. There will be a few questions for you to practice this equation in this week's quiz. The next thing to look at is the Maxwell-Boltzmann distribution, and it's a graph that shows you how the speed values of all the molecules in your gas are distributed. So it tells you what is the most probable speed, what is the maximum speed that molecules will have. So we'll have a quick look at the simulation to see how this works. So here we've got some molecules in a gas. This is modelled as an ideal gas. And if you look at different molecules, you can see that different molecules have got different speeds. There are some molecules moving very quickly, some molecules moving very slowly. But what we can do is we can use statistics to give us a mean value or a root mean squared speed value, or the most probable value, which would either be known as the modal value of the speeds. And this Maxwell-Boltzmann distribution graph shows those range of values. So here we can see we've got speed on the x-axis and number of molecules on the y-axis. We can see here this peak is the most probable speed. This is the most probable speed of the particles. This line here, sort of shifted to the right of that, is where you would find the average, the mean speed of the particles. And then a bit greater than that, a bit further to the right of that, is the root mean squared speed value. You might be wondering, why do we even use the root mean squared speed value? And it comes about from the derivation I spoke about earlier. So if you want to know more about why this is used, then watch the derivation video. If you're happy just knowing that we have to use it, then you don't have to watch that. If we increase the temperature of our gas, it moves the Maxwell distribution graph. So this here is, this orange line is at temperature T1. This blue line is at temperature T2, where T2 is hotter than T1. So this blue line is for a gas that is hotter than this orange gas. Both these gases have the same number of particles, so it's the same box of gas, but the blue line is just where I have heated it up. The orange line is where it is cooler. This is really important. When you heat up the gas, what happens is the peak shifts to the right and it moves down. So you have a greater range of speeds. That makes sense, because if I heat up my gas, the particles are going to be moving around more quickly. They're going to be moving much, much, much more quickly. So you would expect more particles with a higher speed. So when you heat it up, the peak shifts to the right, and it also flattens. Some key points to make sure you have in your notes.